Okay, good afternoon, everybody. So today we will continue on the discussion on general EM. We will try to understand more about it, and some of the questions that has been raised, I will try to address those. So yeah, so it's a little bit a difficult algorithm to understand. So I would again ask you, if you have any questions, you should ask. Okay, so see, in the online mode, if you ask questions, I mean, nobody knows who asked. I mean, we know who asks, but we don't know you really. Like, I have never met any of you physically. So this is a good opportunity to ask without any fear. So, okay, so please do that. So anyway, let's continue. So let me share my screen. Okay, so I hope, yeah, it's visible to everybody. So let's just start today's class. So basically, we had been looking at EM algorithm. So one of the questions that was asked, I think it's a reasonable question. So why not directly try to, why EM? Okay, why is this necessary? So the question is a valid question. So what we had done in MLE, so if you recall in MLE, what did we do? So we directly look at the likelihood, okay, given the data, we write it as this, right? I equal to, let's say 1 to n, okay, f of xi given theta. So this we take the log likelihood. So log likelihood, so this is, I think, written with capital L. It doesn't matter, these kind of notations, I'm not particular as to what you are writing. So as long as it makes sense, it's okay with me. So we take basically the MLE definition is which parameter of theta maximizes it, right? So argmax theta of capital L theta. So in order to find out this argmax, what we typically do is we take the natural log, okay, ln. We take natural log for this entire expression, and then notation, we write it as small l, and this becomes summation, what is this? Log of f of xi given theta. So this is what it is, and then you take the derivative with respect to theta and set it to 0, and that gives us MLE estimate. Okay. So this is what we do in the general case. Now, why are we not doing this at all fully? Why are we not doing this directly? Okay, so the reason is in your machine learning problems, right? So this is a little bit a general discussion, and I think Bhavna asked this question, and it is a very good question. So you will see why. So now, in general, right, whenever you are measuring something, okay, you may not, underlying causes you may not see. Okay, so for instance, if I am, let us say I am looking at ICU patients. Okay, so let us look at a real world example. So you are looking at ICU patients, and you get for every patient you are getting some data. Okay, so every patient at a certain time, I can look at what are their parameters. Okay, so I will measure, let us say, 100 different things for the patient. So it will be x, this is for the ith, yeah, so x1 to x100. So let me write it as capital X, x1 to x100. Okay, these are various parameters. So let us say this is something that blood pressure. Okay, something else will be temperature. Okay, something else, and all these kinds of measurements are there: blood pressure, temperature, and maybe some sugar, some such thing. Okay, so you are looking at several such data. Okay, and now all these data, okay, is coming from some kind of a underlying problem is there, and that problem manifests as some kind of a data. So what I'm saying is, if there is diabetes, so these are underlying causes. Okay, so this is called diabetes. Okay, so there is one underlying cause. So let me call this as Z1. Then there could be another underlying cause, which is heart disease. Okay, heart disease. And then I don't know, some other disease, maybe TB, tuberculosis. So these are all the underlying things. Okay, so they will cause each of these parameters, they will affect in some way. Okay. Now, the problem is you cannot look at this directly. You are not, see, you can investigate and actually find out these things, but in a machine learning problem, you are supposed to infer these things from data, right? So you are only given these 100 measurements. Okay, so you are supposed to infer something about this Z without really having observed it. Okay, so there is, so here, if you see, there is a joint distribution of X and Z. Okay, there is some kind of a dependence that you can find out based on your domain expertise. You can find out how this is happening. All these things you can do from domain expertise. Okay, and you can, if you knew all of these things, all these parameters you can get. So this is a topic called as factor analysis. Okay, so this is also an application of EM. Okay, so there are many applications of factor analysis, but I'm just trying to tell you, motivate why we are trying to do EM in the first place. See, if you are given completely all these Z1, Z2, everything you know, then this is an easy model to estimate. So I can find out theta MLE, which best explains this data. Okay, but the problem is I don't know Z at all. Okay, so I don't know how these dependents are arising. Okay, so basically the problem then becomes, given you have some Z, what is the probability that, so you're given that you have some set of measurements for a particular patient, you would like to find out what is the probability of Z. Okay, so in order to do a problem like this, where there is the data, okay, let us not dwell on this particular example more. I will give you one of this as a like a mini project, and for those of you who are interested can take up that. But in general, when you have data, okay, so there is data good, which you can observe, and then there is data bad, which is hidden or latent. Okay, so now when you have something like this, you cannot use directly this approach to estimate the parameter theta, which best explains DG and DB. Okay, you cannot do this unless you know this fully. If you observe, then you can do, but if you cannot directly do this. Okay, so that is why we have this complicated procedure, which actually is like a iterative procedure, which gives which allows you to learn this theta. Okay, Bhavna, does that answer your question?
Yes, sir. Yes, sir.
Okay, so the whole idea is, there is some things that are not known to you. You need to learn something from the data. Okay, so I will make you do some interesting assignments, some interesting projects where you can explore all of these things. Okay, so yeah, so but I want you to understand the philosophy, and that's why I think this is a good question. So this was the need for EM. Yes, anybody has something to say?
Yes, sir. Sir,
Yeah.
I didn't understand if data bad is the data that is not observable. Then
Yeah.
then how is this helping us? Whereas, like, I understand that if that is not observable, then that will hamper our inferences. But how is this EM algorithm helping us in that case?
Okay. See, EM algorithm is like your clustering algorithm. Okay, so if you, for example, I will do this. You can think of this as okay. So let me just pause and try to answer slowly. Okay, so the question is, if there is something which is not observable, how is the EM helping? Okay, so if you knew the underlying model and if you are able to see everything, there is really nothing to solve. Okay, so basically the whole idea is, you are given some data, there is a plenty of data that is available to you. What is not known is what is the underlying cause that is causing a particular thing. Okay, so what EM does is, it gives you a procedure which is probably going to go towards the local optima. Okay, which means it is going to give you something meaningful. Okay, and it is going to tell you like what is the chance that somebody is having a disease, for instance, that you can get. So it's unsupervised, right? There is nothing that you are having, just plain data. Okay, and a model is what is the important thing. You have to choose the right model. If you choose the right model, it helps you solve a real world problem, which is what I think algorithms are for, right? So Siddharth, what is the issue here? I mean, I specifically don't understand your question.
So in case some data points are not observable, then that, okay, so that was you're referring that it figures out itself that what might be
Yes,
the
yes,
linkage.
yes, yes. So I will tell you, for instance, one particular algorithm which is called as latent Dirichlet allocation. Okay, it's called LDA. It's also called as topic model. Okay, so there is a algorithm like this which you can solve with what is called as variational inference. So now, for those of you who are movie buffs, okay, so there is a data set of English movies. So there is a data set of English movies. Okay, so this is basically what you have is plot. Okay, plot, title, director, all these details are there. Okay. Now, what you can do is you can completely remove this title, directors, and proper names, nouns. All of this you can remove. Okay, and then you can run LDA. So what that does intuitively, without really trying to understand much, let me tell you, it clusters them. So you can, so how, let's not get into, what it does is it puts similar movies together. It will put, for example, there is a movie called as Godfather 1. Okay, it will put Godfather 1, Godfather 2, Godfather 3. Okay, without really using any of the names that are there, just based on the description, it will put them together. It will put Goodfellas together, which is also a gangster movie. It will put things like horror movies. There is a movie called as Paranormal Activities. Okay, and then there is a movie which is called as I don't know, some Ring. Then there is all these scary horror movies are there. What is that? Yeah, some such movies it will put together, and then it will put cartoons movies together, animations it will put together. So this is the kind of thing you can get just based on inference. So using nothing but simple raw data. Okay, why you want to do this? Because there are many problems like this which are of this nature. Okay, so you can think of, see, this is where the machine learning is having so much practicality. Okay, if you choose the right model, you can solve all kinds of problems. Okay, so this is the kind of flexibility you get from this kind of models. So isn't this amazing? I mean, this is a very toy example, but if you want to do something like anomaly detection, right? So what that means is like, so you are processing, let's say you have huge data of customers, you have lots of customer data. So think of them as features, okay? So now, given this entire set of transactions that is happening on a day-to-day basis, there is no way you can look it from your eye and detect if there is any thing going wrong. Okay, whereas if you try to cluster all the transactions together, it will typically so happen that all the bad transactions are like suspicious transactions will be held out separately. Okay, so just based on a proper choice of model, you can do things like anomaly detection. Okay, there are a lot of applications of this hidden variables, and then there is things called as hidden Markov model, which is also solved with EM, where you can use to do some kind of speech processing. You can tell who is the speaker. You can make like some password enter, like you can say things so that it opens. All these things you can do. Okay, you can, yeah, you can do as you speak, it will type. All these things are possible. You can you can do also based on, if I'm writing something, right? Say I'm writing A now, so it will predict what I'm writing, and it will, you can start doing things like this. So there are a lot of applications for these things. So what you need to do is you need to find out what kind of real world problems are these problem solving, and then if you wish, you can do very interesting startups with these kind of ideas. So this is a very powerful field, and what you need to do is you need to find out what are all the problems that these kind of algorithms will solve. Okay, so using just data, you can infer a lot of things. So yeah, so Siddharth, is that okay? What is it clear? What you're asking is, do you get an answer to what you asked?
Yes, sir. It's clear now.
Yeah, so we are just working with simple models, but there are applications are plenty. Okay, so you first learn the technique properly. That is where then you can then slowly explore and try to see where and all it will be used. Okay, so this was some of the questions that people asked, and then there was a specific question about the EM algorithm itself. So that I will now discuss, and then we will try to wrap up EM in this class, hopefully. Okay, so yeah, so let's recollect the steps. So I will not write the full thing. So EM. Okay, so what you are given basically our input is excise. Okay, this is your observable data, and then your yeah, this is your observable data, and then what you want to do is you want to find theta, which maximizes the likelihood of which maximizes this likelihood of theta, which is actually equal to what is that? So this is basically argmax of p of x given theta. Okay, so what is a you want to find a parameter theta which best explains this x. Okay, so that is what you would like to do. Okay, so the problem is what is the challenge? Challenge is there are hidden / latent variables. Okay, so this is the challenge. So one of the applications where this happens is a mixture. So the one application, okay, it's just one application. Please remember that there are many ways you can use this. One of the application is a mixture of distributions. Okay, so in a mixture of distributions, what you have is there is a k, okay, and that k tells you how many clusters are there. And then you have f of xi given a particular theta j. What is the, if it belongs to jth cluster, how is f of xi coming? So this is what is given. So this is one application. Okay, there can be many applications. All you need essentially for using EM is that there is some data and there is some things which is latent or hidden. Okay, so that is what EM is. It's quite general. It's not just for a mixture of distributions. So this is what is given to, this is what is the problem framework. And then what you are doing is very similar to what happens in k-means. Okay, so what happens first? So you random initialization. Okay, random initialization of theta 0. So this is randomly chosen. Okay, this is the first step, and then you repeat till convergence. The first step is called as a E step. Okay, here you will first, so in this particular EM, I'm assuming, okay, assuming ZIs are hidden. Okay, I'm assuming that. It can be something else also, like YIs are hidden or something, but for the sake of notation, I'm assuming ZIs are hidden. Okay, so what do we do in E step? We find out, basically we find out what is called as Q star of Z. Okay, which is basically the probability of seeing this hidden things, assuming your data and your previous parameter. Okay, this is what is the assumption. So this is called as Q star of Z. Okay, so this is somebody had a question here. So what does it mean? Okay, so what is Q star of Z? So I will explain what does it mean in the context of mixture. Okay, so in the context of mixture, what you are interested is like, if you remember k-means, right? So you had a few points, and then you had a few points like this in k-means. Then you choose some random things as centroid. This one and this one I can choose as centroid. So basically, what EM does is it will find out which are the nearest things, and it will forcibly assign one of these all these points to one of these clusters, right? So these points will be in this cluster, and these points will be in this cluster. So something like that. This is the centroid. The darkly shaded thing is the centroid. So if you were to do this in a hard assignment, what you get is you get Zij's, which is equal to 1 or 0. 1 if I belongs to jth cluster. Okay, so this is what you have, right? 0 otherwise. Now what we are trying to say is, instead of doing hard assignment, let us do soft assignment. Okay, so what we will say is, let us ask what is the probability that Zij is equal to 1. Okay, that is the question that is being asked. Okay, instead of doing this one, and this thing we are going to call it as QZ. It's a distribution on the Zij's. Okay, and in the E step, what we are setting is, we are setting the best Q star, not the best, but in the E step, what we are doing is we are setting the distribution for Z, which is depending upon the previous parameters. It is just setting this Z. So yeah, so this is the Q star. So somebody whoever asked this question, is it clear to you what's happening here?
Yes, sir.
Yes, it's just a simple posterior. Okay, so you are just trying to find out what is the probability that you see a particular Z. Okay, and how do you get that probability? It's based on whatever data you have seen and what is your previous estimate. So that is theta t. Okay, so now using this, we can estimate what is called as Q theta Q star of Z. Okay, so this this is given by the expectation which is taken with respect to Q star of Z. Okay, log of okay, so this is a tricky thing for you to understand. Okay, which is quite this is the most complicated step in the EM algorithm, but let me just try to clearly tell. So basically what happens here, it is that you look at theta as a free variable. Okay, so choose theta as a free variable. Okay, so what does that mean? So you are not fixing any particular theta. So theta, like in you when you see the log likelihood, right? So where was this expression here? Right here, what is the meaning of theta? So this is like if you fix a value, you will get a number, right? In the same way, we are treating this theta as a free variable. Okay, and we are taking the joint likelihood for this parameter. So now the question that arises is what is the expansion of this? Because that is when you will really understand this. Okay, so let us do that. So because Q star is a function of theta t, the previous iteration, this is also sometimes referred to as Q of theta t. Okay, so this is what sometimes they refer this to. Now let me write what is Q of theta t. So this is not part of EM, but it's just an explanation that I'm going to give you. Sorry. So this is going to be sum over I, sum over J. Okay, so this is whatever I'm writing is for the Gaussian mixture. Okay, this is for Gaussian mixture or mixture densities. Okay. For other problems, it will be having a different formulation. So here I will have P Zij equal to 1. Okay. So what is the probability that Zij equal to 1? This is what I have computed here. Okay, this is given by Q star. Okay, so this is what is that number here, and then I will just take log of the log likelihood, the joint log likelihood, the full information thing that we discussed, right? So this one x comma z. Okay, so xi comma zi, and the zi I am taking it equal to j. See, what is the necessity? Why I am not taking xi equal to something? Because that is observed. This you know perfectly. You don't know whether zij is the ith value of the zi, which cluster the ith value belongs to, that you don't know. That is why we are taking a probabilistic view. Okay. So now this entire thing is assumed to be dependent on the theta variable, which is the free variable. Okay. Now if you see, this expression is easily solvable. Why is that? Because now you know everything here. This is now back. This is a for a theta, this is fixed. Okay. And then it is the complete log likelihood. The problem of log of summation goes away. Okay, everything is known here. So then you can solve this and you can get that is the M step. So this is the E step, and in the M step, what I do is I will do theta t plus 1, which is argmax over all the possible theta of Q theta t. So these are the two steps, E and M. Okay. So this is how did we derive this? So if you recollect how we have had a discussion, we started with a Gaussian mixture model. What we did in that Gaussian mixture model was we took the likelihood as it is. This thing we directly tried to maximize, and that gave us to some form. Okay, that gave us a particular form for the Gaussian mixture model. And then we realized that the gamma ij's that came there, that is actually like a probability. Remember, that is where we started, and we have written Q star, which is kind of mimicking that gamma ij. Okay, so that is how we wrote that. And then we understood that the M step is taking the maximum value, like for the expected log likelihood. Okay, so this is what we did in GMM, and that's how we got this algorithm also. But what is the important question here? What is the thing that we really need to ensure that this is okay? Yes, somebody wants to say, what do we do with this? I have got this completely based on an example from Gaussian mixture model. But if we really have to use it, we have to do something. What is that is missing here? Yes, what do I need to do to ensure that this is all right? Manan, what do I need to do to continue?
Sir, I don't have an idea.
Okay, so are there any questions, Manan? Do you follow what is the algorithm in the whole discussion that we are having?
Yes, sir. Like, yeah, I follow the algorithm, like what we are trying to do.
Okay, so basically we have got this algorithm by looking at a particular example of Gaussian mixture model. That is also clear to you, right?
Yes, sir.
So, but what is missing is we need to show that it actually works. We need to say that it actually gives us what is desired. What was our desired thing? We wanted to explain, we wanted to find that value of theta which maximizes this, right? So we need to do that. So that is the question that we are asking. Okay, so we need to check for its correctness / convergence, whether it really converges to the true value. So this is the question mark. Okay. So before going to that correctness or convergence, let me just quickly ask if there are any questions. So can I have a quick poll in the chat if you are following all the discussion so far? Can you please say if it's clear? Can you say yes? If it is, if you are having questions, you can tell me and then we can discuss. Okay. So this is a important algorithm. You will see that. So. So Viranch, Viranch is there?
Yes, sir.
So do you have any questions?
So I have to refer this one more time because I have a doubt in, I'm not getting what exactly that Q is doing.
Okay, it's a good question. So you please feel free to ask. Okay, so this Q, is it capital Q?
Yep. Yes, sir.
So did you understand what is small q?
Yes, sir.
Okay. So now what we are doing is, so basically we have the full information case. So you remember, Viranj, what is the full information case? Yeah, so basically in the full information, we are knowing the hidden variables also. Okay, so in the full information case, if you forget that there is this probability, okay, if you forget this entire thing, so let me just copy this and we will discuss. See, I want people to ask questions, okay, because that will help everybody. So let us see. So coming to this, so in the full information case, you have xi's and you have zi's. Okay, so now when you look at the likelihood, okay, for your entire data, so this is your D. Okay, so this is going to be given as product I equal to 1 to n p of xi zi given theta. So now Viranj, so if you look at this, right, if I vary theta, I will get different values. Is that okay? Do you follow that idea?
Yes, sir.
So this is like in your Bernoulli, if you had two heads, right? Two heads and a tail. Okay, and if I take p equal to 0 or p equal to 1 or p equal to 0.5, I can have a plot of the likelihood of p versus this particular data, right? So then if you do that, you will get that it peaks at 2 by 3. So as a function of theta, I can plot the likelihood. In the same way, I'm saying this L of theta is a function of theta. Okay, so if you plug in a value, I can give you the output. So you tell me what is theta, I will tell you what is the likelihood. Okay, this is so, but the good thing about this is, since you have some form like this, you can use Bayes rule and write this as P of Zi into P of Xi given Zi. Okay, so that theta is always there. So let me write this properly. So this I can write, and then if I take log, okay, so if I take log on both sides, I get the small l. I will have a summation of I equal to 1 to n, okay, and log of again some more summation log. So it will be like completely summation form. Okay, so I will get something like this. Sum of some terms. In the example that we took, it will have pi j, then plus so some pi j plus ln something else and like this. But the things are all the parameters have cleanly separated, and then I can do theta MLE easily. So this is okay, right, Viranj, so far?
Yes, sir.
Okay, now what is the challenge? See, now we don't know what is the value of Zi. Okay, we don't know this. This is hidden. Okay, so sorry. This is hidden to us. So instead of, we cannot directly solve this. So what we do is we take an expectation. Okay, so since we don't know what is Zi, what I will do is I will take an expectation of the log, the joint likelihood like this. So I will take expectation like this. Okay, and what is the thing that is unknown? I don't know what is Z. So I will assume that Z has a distribution which is given by Q star of Z. Okay, so I will do this. So now, what are all the things that this is a function of? Can you tell me, Viranj, what are all the things this thing depends upon?
Z, yeah, Z is
Z means the distribution of Z. What is the Q star you are assuming? Okay, right? What is the distribution that you are taken for this? And what is theta? Together, if I give you this both, you will tell me a number, correct?
Yes, sir.
So this is what this Q represents. Okay, just see whether now it makes sense to you.
Yes, sir.
Okay, fine. Okay, so that was, I hope, useful for everybody. Anyway, so now coming back to correctness, let me just quickly see in the chat if there are any more questions. Okay, so yeah, so now coming back to the correctness, so let us do that now. Correctness / convergence. Okay, so what we will do is we will do some algebra, and then you will understand how the correctness is happening, how the algorithm is actually going to give us a better and better outcome in every iteration. That is what we are going to do. So the first thing that we'll observe is that P of X given theta. So this is basically what I am trying to maximize, right? So this is the probability, this is the likelihood, okay, of the data given the set of parameters. I want to maximize this. Okay, so this is equal to P of X comma Z given theta divided by P of Z given X theta. Okay, so so now what is the value of Z that I have to choose? This is true for any Z. Okay, for all Z such that this denominator is not 0. Okay, so this we will assume is true for the entire problem. This thing we will always assume. Okay, so this is always given. Okay, if there is some Z which is exactly 0, that is not like a rich model, so we will ignore that. Okay, so this is true for every Z. Okay, this is what is called as Bayes rule. Let me remind you what is the Bayes rule again. So P of A given B is P of AB divided by P of B, right? So it is also true even with this conditioning. So so what I'm trying to say is P of, sorry, not writing legibly. So P of A, B, and E, if I want to add something, it's also true as P of A comma B given E divided by P of P given E. Okay, so this is also true. Okay, so I hope all of you remember the conditional probability idea that we have discussed. Okay, so if you have not, if you don't follow this, you can just go and check some of the lectures that was done in the last semester. You can just quickly refresh. But the idea is very simple. Okay, so I hope you can see the correspondence between this and this. Okay, so yeah. So now if I take log, okay, so this is log of P of x theta is log of P of xz theta minus log of P of z thing. Okay, so this is also true. Fine. Yes. So this is just taking log on both sides. Now what I will do is, see, this is for all z. Okay, so for every z this is true. So what I will do is I will take expectation for z with respect to some q. Okay, so I will take expectation for the z with respect to some q. That is what is the next step. Okay. So this is not a function of z. So if I take expectation with respect to qz on both sides. So what do you get? So left hand side is not a function of z, it's a constant. So this will be ln of p x theta. Okay, so now we have expectation of this. Expectation of this will be over all the z. Okay, qz ln what is that? P of xz given theta. Okay, so this is the first term. So there is no expectation, sorry, because all this is the whatever I have written is the expectation. Okay, so this is what we will get on the first term, and on the second term again we will have over z qz ln of p z x theta. Okay, so this we can do. So what are we trying to do? Again, trying to remember, we are trying to prove the correctness of our EM algorithm. Okay, what we have got as an EM algorithm is based on an analogy between Gaussian mixture model. That's how we got the EM algorithm, but we have to show that it is actually correct. So that is what we are doing right now. So now we will do some small trickery. So we will write this as so did you follow what we did? So basically we multiplied and divided by qz. Okay, so if I multiply and divide by qz here, so one of the qz terms I will combine with the thing here. Okay, so if I expand this, right, I will have qz ln qz, negative ln qz ln qz here, and a positive ln qz, positive qz ln qz, which will cancel. So basically I have added and removed with some number. Okay, is that all right? Yes, I hope it's okay. So now on the left hand side is the quantity that we would like to minimize. On the right hand side we have these two terms. Okay, so these two terms have special meaning. Okay, so this is we will call this as L q theta. It is depending on the q that you have chosen. Okay, and the right hand side we will call it as KL divergence between, okay, KL divergence between q and p. Q and P. Okay, P of this thing z given x theta. Okay, so this is this. So this ln L of q theta. This is equal to this term. Okay, just naming them and KL divergence is negative this term. Okay, so now in order to prove the correctness, we have to understand the KL divergence a little bit more. Okay, so KL divergence, which is also called as, okay, I may make some spelling mistakes, but it is Kullback. Let's see if I have the book somewhere. Okay, it's okay if I make mistakes, but Leibniz. Okay, KL divergence. Let me see. I don't want to have a recording of making a mistake. So let us see. Can someone check if this is the correct thing? Yeah, Kullback, Leibler. Okay, divergence. All right. So what it is representing is it is like a distance between two distributions, two probability distributions. So what does that mean? So if Q and P are two distributions, so okay, so first let me ask people. So P of Z given x theta is also a distribution on Z. Q is also a distribution on Z. Does everybody understand this idea? Q is a distribution on Z, right? Because I'm taking Z, Q, Z, that is also clear. Even P of Z given x comma theta, it is a distribution on Z. Is this idea clear to everybody? Okay, so both are the distribution on the same set of things, same set of values, okay? So it depends upon what values this Z's take. Okay, so the distance between two probability distributions is going to measure how different Q and P are. Okay, so it satisfies some desirable properties. The first thing, if I'm saying something is a distance, what should KL of Q with respect to Q be? Yes, if it's a distance, what it should be?
0.
Yeah, so then let's try to see if this is true. So we will take the definition. So KL of QQ, okay, is equal to minus summation QZ ln of QZ by QZ. Okay, so what does that give? Yes. What is ln of 1? Log of 1?
0.
0. Okay, so this entire thing is 0. So this is good. Okay, so does everybody see this? So this is good. So property number 2, see, distance has to be positive. Okay. So this is what we will check now. Is that okay? So the distance takes the value 0 when you are taking the distance between the two things which are actually the same. Okay, for all other values, it has to be greater than or equal to 0. So this is the second property. All right. So that is what we are going to show next. That distance between Q and P is greater than 0. So for doing this, okay, we will use what is called as Jensen's inequality. So let me just change color because we have been, okay. So Jensen's inequality, Jensen's. Okay, for that, to understand Jensen inequality, we need to understand what is a, okay, so I don't know which version we are using, but anyway, we need to understand what is convex functions. Convex functions and concave functions, both of that we have to understand. So if you, let's try to understand what is convex functions. So convex functions are functions which have a shape like this, okay? So they have a shape like this. So this is not a very mathematical way to tell anything. So this is a function f of x. Okay, so the definition of a convex function is if you take any 2 points, okay? So this is, let's say this is f of x1 and this is f of x2. And if you look at the line joining any 2 points, okay, the line segment connecting these 2 points, so that values will be given by lambda times f of x1 plus 1 minus lambda times f of x2. Okay, so if you put lambda equal to 1, you will get this point. If you put lambda equal to 0, you will get this point. Okay, so lambda has to be a value between 0 and 1. So as you vary this one, you will get a line that is connecting these 2 points. Okay, and if you take a particular point over here, which is here, the value at that function takes. So that is nothing but, so this point over on the x-axis is x1, lambda x1 plus 1 minus lambda. So I'm sorry, I have done small mistake here. What I meant to say is this on the x-axis, this is x1 and this is x2. Okay, and this value is f of x1, and this value is f of x2. The intermediate value is this. Okay, this is the intermediate value, which is lambda fx1 plus 1 minus lambda fx2. The corresponding point under that curve, if you draw straight, it is 1 minus lambda times x1 plus 1 minus lambda times x2. What convex functions have the property is that f of lambda x1 plus 1 minus lambda x2, this is going to be less than or equal to lambda times fx1 plus 1 minus lambda times fx2. Okay, and for concave functions, the property is opposite. So let me draw that as well. For concave functions, you have the opposite nature. Okay, so this is again the same thing, but I will not try to again explain this. But f of lambda x1 plus 1 minus lambda x2, okay, this is going to be bigger than the line. So the line joining any 2 points is under the curve or above the curve. For concave functions, it is under the curve. Okay, the curve goes above, and this is true for all x1 and x2, by the way. Okay, this has to be true for all x1 and x2. Okay, so does everybody understand the definition of convex and concave function? Yes, is it okay, this definition, convex and concave? You might have seen this already, right? If you have taken optimization, you would have seen this thing. Anyway, the point is the course also applies for others who have not taken, so I'm asking them specifically. I hope this idea is clear. So either the line segment lies above the function or the line segment lies below the function. Okay, so examples of convex functions. So convex function examples. So f of x is equal to x square is an example. Okay, this is one example. And concave functions, f of x equal to
so minus x square.
Yeah, minus x square is also an example. Yeah, so if you just flip it, you will get a concave function. Okay, so that's good. But there are other examples also. I think I don't know. How about log? How does that look? Can someone tell me the shape of log x? So at 1, it takes a value 0. Okay, and
Convex function.
it's a convex function, is it?
Concave.
Yeah, so I think it is concave. We can check by taking the second derivative. Okay, there is a test for doing this. You take the second derivative of this, what you will get. So if you take second derivative,
Sorry, concave, sorry.
you'll get 2. Okay, so convex functions have positive second derivative and concave functions have negative second derivative. So let us do that. So d by dx square of ln x, okay, is d by dx of 1 over x. Okay, it is minus 1 over x squared. So it is negative. So this is a concave function. So this is ln x. See, it's okay. We don't have to memorize anything. See, we are not, I don't want to name subjects, but we are not trying to memorize things. This whole course, everything that you do in engineering is not about memorizing. Okay, if I'm teaching you something which is making you memorize stuff, that is really not desirable. Okay, so it's okay if you make mistakes, if you don't remember, we can always derive it. Okay, so anyway, so this is the whole discussion. So we wanted to talk about Jensen's inequality, but before that, we had to understand what is convex and concave functions. And what Jensen's inequality gives us, so for we will focus on the convex functions. Okay, for example, let's say example f of x equal to x squared. Okay, what it says is expected value of f of x. Okay, expected value of f of x. So if you come back to the function, right? So expected value of f of x will be something like the line. This has to be bigger than f of expected value of x. Okay. So let's try to understand whether this is correct. So expected value of f of x. So what is that? So let's take an expectation. Okay. So there is a function which takes value half x1, and with a value half it takes x2. So what is expected value of f of x? What do you get? As you vary the probability, you will get points along this line. Is that okay? Do you understand this? I'm trying to give you an intuition on the Jensen's inequality so that you don't have to memorize it. Okay. So as you vary the probability, when it is 1, the expectation will be here. When it is 0, when this is taking value 0, the expectation will be here. In general, it will take a value along this line. Okay, because you are taking p into x1, sorry, p into f of x1 plus 1 minus p into f of x2, which is exactly this. So lambda can be treated as a probability. Okay, so when you treat it as a probability, you'll get a line like this. So for convex functions f, okay, this f of expected value of f of x is greater than f of x this one. Okay, so what is this? So this is, if I take the example, for example, expected value of x square is greater than expected value of x whole squared. Okay, can someone tell me why this is true? Is it true, first of all? For any random variable x, I'm claiming Jensen inequality says that this is true. Can someone verify this for me?
If the function is fx is equal to x squared, then it's convex. And then...
No, that is true. That is just applying the definition. But I am telling you, without using Jensen inequality, can you show this?
Sir, if we take this expectation of x whole square on the left hand side, then it becomes variance.
Yes, very good. So that is what it is. So variance of x, if you remember, has two formula. One is expected value of x minus ex whole squared. Okay, so this is one formula. Using this formula, I can understand that variance of x is always greater than or equal to 0. Is that okay? Yes? Someone say something. Is this okay?
Yes, sir.
Yeah. So now, if I this is given to us, but if I expand this and if I simplify, variance of x is also given as expected value of x square, okay, minus expected value of x whole square. Okay, so variance of x is also this. So using the previous inequality 1 on this new form, we get expected value of x square is greater than or equal to expected value of x whole square. Okay, so never memorize anything, rederive if required. Okay, even if it wastes time and you will get less marks also, it's okay. All right, so it's much more satisfying that way. Okay, so that can be understood by even looking at the convex function itself. So if you take any 2 points, if you look at distributions, you are just basically joining the line, and we know that the line always lies above the function for a convex function. Okay, so this is the 2 things that we have shown. For Jensen's inequality for convex function, this is the form. Okay, so what is it that we were doing? We have completely forgotten. So let's come back to that. Okay, so we were talking about KL divergence. Okay, so let's come back to that. So KL divergence between Q and P. Okay, this is given by minus QZ ln PZ by QZ. Okay. So this is if Z is taking discrete values, but if it is taking continuous values, this will be integration. Okay, so nothing major. Whenever you have continuous, it will be an integration. So now we were trying to prove two things that we wanted to prove. One is this we already shown. Q with respect to Q, this is equal to 0. Second thing that we wanted to prove is that P with respect to Q, this is going to be greater or equal to 0. So this is where we wanted to prove, and we discussed the Jensen's inequality. Okay, so now let's try to prove this second statement. So if you observe, right, what is the second statement saying? So this is this minus ln. So ln we have just shown is a concave function. Okay, so ln of x is concave. Why? Because if you take the second derivative, d square by dx square of ln of x, this is negative. Okay, therefore minus ln x is convex. Okay, so if you look at this expression, so I will stop immediately. I will quickly finish now. This is actually the term is expected value. Okay, this is expected value of Q of minus ln P by Q, right? This is what it is. Okay, now I know that this is a convex function. Okay, so we can pull this guy out. Like if you see the function, we can pull out. Okay, so this minus ln I will pull out. This is going to be greater than or equal to minus ln of expected value of Q of what? P by Q. Okay, so what does that mean? So let us try to see what this is. So this is minus ln summation qz into pz by qz, right? So this qz cancels. What I am getting is minus ln of summation pz. Okay, I would have asked you, but summation pz is 1. So this is minus ln of 1, which is nothing but 0. Okay, so we have got what we desired. So left hand side is KL. So KL divergence between Q and P is always greater than or equal to 0. All right, so I will stop here. I know you have class after this, but I will ask you to go through the steps that we have done so far. And if you have any questions, you can ask me in the next class. Okay, so let me stop here. We will continue from this point in tomorrow's class. Okay, if there are any questions, I will hang back to answer. Otherwise, I will see you all tomorrow. Okay, guys, thank you.
Sir.
Yeah.
Sir, in this full information model, we just added a variable z, and we got to know that our model is now is completed. We don't need any other variable. So suppose
Yes.
if there is a model in which along with x there are 2 more things that are required to make it complete, like z or y and something else. So how we come to know that there are this particular number of things that we require to complete the model?
Yeah, very good. So that is a thing that you have to think about yourself. See, for instance, right, you have to come up with a model which you think is actually generating the data. That is something that you have to think of yourself. Okay, but it is a fair question. How do we know? There may be Z and there may be something W, right? So how do we know? But that is a thing that you must know. Okay, so that is how you will do it, because you know something about the problem, so you can guess. Rajnish, is it okay?
Yes, sir.
All right, so let me just stop the recording. If there are any more questions,